Algebra 2 Honors, 5.6b, examples 3 through 6. And so we already had another video on examples 1 and 2, so let's drop down here. And so this first inverse that we did was, in example 2, was the inverse of a linear function. And so we want to move to inverses of nonlinear functions. And this first one, we have a parabola, example 3, f of x is x squared minus 2, but we have a restriction on the domain, and there's a reason for that, and we'll be talking about that in a bit here, but no. But so find the inverse of this function. So what we want to do is start by graphing this x squared minus 2, but we need values of x 0 and greater, so let's just look at evaluating it at a few points. And so if I put 0, I have a negative 2. If I put in 1, I have a negative 1. If I put in 2, 4 minus 2 is 2. If I put in 3, 9 minus 2 is 7. And so if I'm going to go ahead and graph the function. So we have 0, negative 2, 1, negative 1, 2, 2, and 3, 7. So it's a parabola, so it's going to be concave up and going through those points and continuing, but it's got a restricted domain, so it's just half of it. And so then if I go ahead and do the inverse of this, the x and y values are going to change. So x and then the inverse, I'm going to have negative 2, 0, negative 1, 1, 2, 2, and 7, 3. Those are going to be ordered pairs on the inverse. Let's go ahead and use a different color for those. Let's do that in blue. So now if I go to the right, or to the left 2, I'm at 0, negative 1, 1, 2, 2, and then 7, 3. So that graph is going like that, and that is the inverse. Remember, ordered pairs on the inverse switch, x and y switch. Domain and ranges are switching. And remember that inverse functions are reflections over the line y equals x. If I kind of put in that line y equals x, going through the points where x and y have the same values, there's that line y equals x. These are reflections over that line y equals x. And so as I'm looking at this, I can talk about domain and range as well. The domain on this f of x was 0 to infinity, and the range came out to be negative 2 to infinity. And so since x and y switch, the domain on the inverse is going to be what was the range. So the domain is going to be negative 2 to infinity, and the range is going to be 0 to infinity. And you can check that out on that graph, and it is agreeing with that. When you go to actually find the equation of the inverse, we have originally y is equal to x squared minus 2. We switch x and y, and we solve for y. And when you take the square root, you get plus or minus. However, it's not both of those. It's one or the other. And you have to figure out which of those agree with the range being 0 to infinity. Which one's going to give me a range? And 0 to infinity is positive, so the inverse that belongs to the x squared minus 2, where x is greater than or equal to 0, is the positive square root of x plus 2. That's the one that's going to give me a range that's positive, so that is the only half of that we take. And that is the inverse of that function. All right, so inverses, some other things about inverses of nonlinear functions. The reason why we restricted the domain on example 3 is if I don't, and I look at this x squared. So I've got this x squared right here. If I actually graph its inverse looks like this, and the inverse fails the vertical line test. And if you remember back, if it fails a vertical line test, it is not a function. It is not a function. So the inverse of x squared is not a function because it fails the vertical line test. And so when I use the notation f negative 1 of x, that f inverse, that means function. And so that's why in example 3 we only took half of the parabola. If I only take half the parabola and reflect it, the reflection will pass that vertical line test. Every place I think about putting a vertical line, it is only hitting that once, and so therefore its inverse is a function. So what we talk about, this is not a function. What it is we would say it's an inverse relation. It just isn't an inverse function. Now, on the other hand, if we look at x cubed, so we have this parent function here of x cubed, so it's going like this. There's that x cubed function. Its inverse actually is a function. Its inverse is right along here. And this inverse, the cubed root of x, is a function. It passes that vertical line test. Any place I put a vertical line test or vertical line on it, it is only hitting at one point. So this inverse is a function. And so we're going to look at, well, how do I know? If I look at the original problem, so if I look at the x squared, if I look at the x cubed, how would I know to expect if its inverse is a function or not? And that's on this next page. And so we have what we call the horizontal line test. This horizontal line test. The inverse of a function is also a function if and only if no horizontal line intersects the graph more than once. So we use a horizontal line test on a function. So look at that. This first example looks kind of like the y equals x cubed. If you take that y equals x cubed and you think about a horizontal line hitting it, it's going to hit that only once. And since the horizontal line hits the function only once, its inverse will also be a function. We say that the function then is 1, 2, 1. Each x is assigned exactly 1 y, and each y is assigned exactly 1 x. Versus, if we have y equals x squared, it fails the horizontal line test. And when it fails the horizontal line test, that means its inverse is not a function. Y equals x squared is a function, it passes the vertical line test, but since it doesn't pass the horizontal line test, its inverse is not a function. So that's what we're going to be doing to determine if a function's inverse is a function. Look at example 4 here. Consider f of x is 3x cubed minus 2. Determine whether the inverse of f is a function, then find the inverse. And so what you're going to do is graph it. So we're going to look at y is equal to 3x cubed minus 2. The parent function on this is x cubed. And so if I have negative 2, negative 1, 0, 1, and 2, I have a negative 8, a negative 1, a 0, a 1, and an 8. So there's your parent function for an x cubed. And the 3 is a vertical stretch by 3. That means we need to multiply y by 3. And the minus 2 is you're going to go down 3. So you're going to subtract 3 from y. And we need to do it in the order that it's written left to right. We need to do the vertical stretch first. So multiply the y's by 3. And then subtract the 2. So my end set of points on this are these. And then graph it and see if that resulting graph passes the horizontal line test. So I'm not going to get all of this in here, but if I go to the left 2, I'm way down at negative 26. To left 1, I'm down 5. And then 0, 0, 1, 1, and then at 2, I'm up at 22. So this would be going like this. Oh, I forgot to go down 2. I was going to say I did something funny. Sorry about that. So I forgot to subtract 2 from 0. I bet you were wondering. So it doesn't go through that 0. It goes through at negative 2. That's going to be better. I knew something was feeling funny. All right, so it's going to look like this. So negative 1, negative 5, 0, negative 2, and 1, 1. And it passes the horizontal line test. If I draw a horizontal line test or a horizontal line anywhere, it passes only one. So yes, its inverse is a function. And so you need to state that because that was part of the problem. And it says then find the inverse. So the process to find the inverse is we take y is equal to 3x cubed minus 2. We switch x and y, and we solve for y. So add the 2, divide by 3, and then take the cubed root. So all right, y is the cubed root. And we'll let you leave it like, well, I'm not going to let you leave it quite like that. I want you to replace with the inverse notation. And so there is its inverse. All right, so example 5. Consider this function, determine whether the inverse is a function, and then find its inverse. Well, this is your parent function. Is the square root function. So we're going to start with those 5 points. And this is a vertical stretch by 3. So you need to multiply y by 3. And this is left 4. So subtract 4 from x. Since you are ending up doing one thing to the x's and one thing to the y's, you can go ahead and do that each column and just come up with the final set of ordered pairs. So the vertical stretch by 3, multiply y by 3. And then subtract 4 from the x's. And then go ahead and graph that and see what the graph of that looks like. Now you're just sketching a graph of this, so we're at -4, 0. And at -3, we are up at 3. 0, we're up at 6. And at 5, we'd be up at 9. Something like this. So it's that stretched out, and it looks like this. And this graph is going to pass the horizontal line test. Any place I draw a horizontal line, it hits it only once. So yes, it's inverses of function. Why? It passes the horizontal line test. So that's part of your answer. And then it says find the inverse. So we are going to have y is equal to 3 square root of x plus 4. Switch x and y. And then divide by 3. And then I'm going to come up here and I am going to square both sides. And I get y is equal to x squared over 9 minus 4 equaling y. And so then, right, that inverse is x squared over 9 minus 4. Now, the interesting thing about this one, though, is you square both sides, so you actually got some extraneous solutions. You got some extra solutions. You have to think that on this original function, f of x, the domain was -4 to infinity, and the range was 0 to infinity. So on the inverse, on f inverse, you need the domain to be 0 to infinity. And so that means you need to say that x has to be greater than or equal to 0. Because otherwise you could put negative values in here. You need to, this is a parabola and we only need the right-hand side of it. We can't take both. If we take the entire parabola, this is a 1/9 x squared minus 4. It's a vertical shrink by 1/9 and down 4. If I don't restrict the domain on this, I have something that is not the actual inverse. So you have to show that restriction. And I think the easiest way to do that is to think about what was that range on the original function and consider that has to be the domain of its inverse. It's kind of in reverse of what happened in example 3. In example 3, we took only half of the parabola so that its inverse would be a function. And then we got the inverse, the blue function, looks like that square root function. It is a square root function, just shifted to the left two. In this example 5, we started with a square root function, and as you found the inverse, you squared both sides, you got an extraneous piece. You got the full parabola, and you have to limit the domain on the parabola so that you have the correct inverse. So we need that x greater than or equal to 0. All right, so we've looked at finding the equation, given one function, graph it to see if its inverse is a function, and then find the inverse. Well, if I'm given two functions, so in example 6, I'm giving 2x plus 4 and x minus 4 over 2. I want you to show me algebraically whether these are inverses or not. So you need to pay attention here. What we're going to be doing in this is we have to show f of g of x, that's how we talk about that, f of g of x. We have to show f of g of x is x, and it's an and, it's not an or. You can do what, you can't just do one or the other, you have to do both. You have to show g of f of x, g of f of x comes out to be x. And you have to show this algebraically. So what that means, we're going to start with this f of g of x. And we want to show that this comes out to be x. And what I have to do is in here, I want to put g of x in for x into function f. What? I want to put g of x every place I see an x in the function f. I'm going to replace the x's in f with the complete g of x function. G of x is this. So replace g of x with its function. Excuse me. And that means in f of x, where I see x, I am going to be putting this x minus 4 divided by 2. Right? F of x was 2x plus 4. And I am replacing that x with the x minus 4 over 2. So we're actually putting g of x into f every place you see an x. And then simplifying. So when I multiply these, you can think of it as 2 over 1, the 2's cancel, and I have x minus 4. You have to show enough steps. And then so I just showed that f of g of x became x. But that's not sufficient. I have to also show that g of f of x comes out to be x. So I'm going to come up here and get rid of the shading and start over with that. And I'm going to pick a different color. Let's do green. So right here I see f of x. And f of x is this expression. So I am going to put 2x plus 4 in for f of x. That means for every x I see in the function g, I am going to replace the x with the expression 2x plus 4. Once again. That means for every x that I see in the function g, I am going to replace that x with the expression 2x plus 4. So where do I see x? I see it right here. So that x in g of x is going to be replaced with 2x plus 4. So I have a fraction, and the x gets replaced with 2x plus 4. We still have another minus 4 and a 2 because it was x minus 4 over 2, and this x had to be replaced with the 2x plus 4. So simplify, the 4's cancel, show itty-bitty steps because you are proving that these are both coming out to x. So you just showed g of f of x came out to be x. So that you wrap it up by saying, since f of g of x equals x and g of f of x equals x, f and g are inverse functions. You have to formally show it. You have to show step by step. It has to be very organized and detailed. Example 7. Find the inverse of the function that represents the volume of a sphere, and then find the radius that has a volume of 288 pi inches cubed. So we have the volume is 4/3 pi r cubed. In this case, I want the volume to stay volume and the radius to stay radius, so I'm not going to switch the variables, but what I'm going to do is solve for r. Because basically that's what you're doing, you're solving for the other variable. So I'm going to start by multiplying both sides by 3. And then I can divide by 4 pi. And then I'm going to take the cubed root of both sides. And so on that one, we've got the radius is the cubed root of 3 times the volume over 4 pi. And they had you do that because on the first equation, the independent variable we would think of as the radius. And so I would produce, given different radiuses, different volumes. But on the inverse, the output is the radius, so if I know volumes, I can plug in the volume and the output's going to be the radius. And they want you to see that that's a way of rearranging this formula and using it a little different. So I've got the radius being that cubed root of 3 times the volume over 4 pi. And they said find the radius when the volume is 288 pi. And so the pi's will cancel, and I'm thinking 4 might go, 4 goes into 288, goes into 28.7, and goes into 8 2 times. And so that radius, I'm going to think that 72 is 36. Well, I'll just prime factor it. 2 goes into there 36 times, 2 goes into there 18, 2 goes into there 9, and then 3 and 3. So you'd have a 3 times a 2 times a 2 times a 2 times a 3 times a 3. So for every group of 3, you can bring a 3 out, and for every group of 3 of 2s, you can bring a 2 out, and so the radius must be 6, and we have units 6 inches. So I just simplified it without using a calculator. That's all. That's it.